Okay, this chapter is about regression. And in this chapter, we're going to talk about what the regression is. Okay, so basically, regression is a statistical method to find the relationship between the variables, between the x and y. Okay, and then we're going to talk about the linear regression, and especially we're going to focus on how to drive the solution. Okay, so we can drive the solution based on the least squares or based on the maximum likelihood. So the solutions are equivalent. And then we will talk about some nonlinear functions, because a linear regression is a linear model of the parameters. Okay, so we can apply the nonlinear function to input x. Okay, so then the regression might be nonlinear, but still it is a linear regression because it is a linear combination of the parameters. Okay, so we're going to talk about that later. And then we can include a kernel approach in regression too. So in PCA, we adapted a kernel method to drive a kernel PCA. So likewise, we can extend the linear regression with a kernel. So it's kind of straightforward extension. And then the last one is, in a sense, it is not a kind of regression, but the name includes regression. So we're going to talk about this logistic regression. So basically, logistic regression is all about classifications usually, but since it is regression, so we're going to talk about it. Okay. So first of all, what is regression? So regression is a statistical method to find the relationship between x and y. Okay, so the goal is to predict the target y given a d-dimensional vector x, as usual. Or we can understand regression as to estimate the relationship between x and y, as I said. Okay, or in other words, we can find the function from x and y. So basically, these three items are saying the same thing. And usually x is independent variable and x is features or x is predictors. And y is dependent variable. So x is independent variable, which means we want to estimate y from x. Okay, so usually in the training, yes, we have x and y, but in when we predict, then the x is given and y is unknown. Okay, so from x to y, but people might get confused with this kind of relationship with the causal relationship. So in regressions, we don't find the causal relationship. We actually provide this relationship first, which means we want to find the relationship between x and y, or from x to y, which means we have x and we have y. So it looks like a causal relationships, right? But the regression analysis cannot find this kind of relationship. Actually, we provide this order. If you want, you can try this. Okay, so if we provide this order, then regression will find the relationship between x and y. If x is function of y, then regression will find the function f. Okay, so the order is given by the programmer. Again, don't get confused with this regression, the relationship that the regression finds and the causal relationship. And in general, a causal relationship is not easy to find. Okay, and the most of the time, machine learning algorithms don't talk much about the causal relationship. Most of the time, machine learning algorithms try to find the correlation or something like a mutual information or something. So there is no direction. Okay. Again, if you define y is f of x and f could be some parametric model, then the regression will find this f. Okay, so in this case, we assume that x is causing y. Okay, but again, regression doesn't find this causal relationship. It is just finding this function. Okay, and there are lots of examples of regression because regression is a really popular method. We have a couple of examples to name of just a few. Okay, and the first one, CPU processing time. Yes, we can predict the CPU processing time based on some independent variables like the amount of memory space or the number of processes or the type of softwares and so on. Okay. Oh, and the next example is battery time on your smartphone. So you can estimate the battery time, how long we can use your smartphone. We can estimate this battery time based on the number of touches or based on the number of softwares, apps, or and so on. Okay, and also typhoon path can be estimated based on regression. Okay, and so on. There are a lot of examples. And in this graph, we have x, which is independent, and we have y. Or when we have a label, then sometimes we use label t. So they mean the same thing most of the time. Okay, so we are interested in finding this kind of relationship. In this case, this is a linear, but sometimes we want to find something like this. And function approximation is a really good example of regression. Function approximation is usually is a curve fitting. So let's say we have lots of samples like this, then M in these figures, M indicates the degree of model complexity. Okay, so when the M is 0, then it is just constant. Okay, with just constant, we estimate, we define this relationship between x and y. Okay, and in this case, this red line is our estimation. Okay, probably this is just the mean of these labels. Okay, and then if we increase the complexity, then this is a linear. In this case, this is just y is a. In this case, y is ax plus b. So we have more parameter. Okay, then if we increase one more time, increase the complexity one more time, then we can use quadratic. We can increase the degree of polynomial equations. Then we can have a better fit to the training samples. But if we increase further, then this red curve can fit the training samples perfectly, but this is not what we want. This is too much. Okay, so we don't like this. Basically, we like a smooth curve of the model, something like this. Okay, as you already noticed, the black curves are the true function from which the samples were generated. So usually we don't know these true functions. We only have these training samples, and then from these samples we have to estimate. We have to discover, okay, the true function. We have to approximate the true function. Okay, so as regression models, so we're going to talk about linear basis function models. Okay, so before talking about the regression, then what is linear? When the function f is linear, then it satisfies this equality. Okay, f of ax1 plus b of bx2 is af of x1 plus bf x2, which means it satisfies the superposition property. Okay, so let's take a simple example. F of x is alpha x. Then ax1, f of ax1 plus bx2 is alpha ax1 plus bx2, right? Then look at this one. This one is alpha ax1 plus alpha b x2, and which is a f x1 plus b f x2. Okay, so when f of x is this simple linear equation, then it satisfies this superposition property, which means we just proved that this function is linear. Okay, and the linear regression is based on the linear functions, this. And y is a linear combination of the parameters. So when we talk about the linear regressions, usually in the definitions, this function is linear function of the parameters. Okay, in this case, we have parameter w. And the simplest linear model is a linear of parameters and input vectors. Okay, this is the simplest linear model. And sometimes, many times, people just, when people say a linear regression, usually, many times, people think this simple case. So given the d-dimensional vector x, okay, then the simplest linear model is defined by this one. So we have parameters, okay, and we have element of input vectors. So this one is actually w transpose x. Okay, it's a simple linear function of w and linear of x. And the linear regression is a linear function of w. Okay. We can extend this model to include the nonlinear function of input. So we're going to change this part. Still, this is a linear because we don't change this one. So this function is a linear function of w. Okay, so we're going to just extend this one to with the nonlinear function. So the basis function models are defined by this. It's basically the same as before. Okay, so in this equation, the phi is basis functions. Okay, it's still linear model of w. Okay, and when the phi of x is just identity function, then it is the simplest linear model. And the w0 can act as a bias when phi sub 0 is just 1. Okay, and as I said, in the simplest case, a linear basis function is just identity function. Okay, and in the simple 1D input, then this is the simplest linear basis function model. And the basis function is feature functions. Okay, from d-dimensional input space to m-dimensional feature space. And the regression is still linear functions from m dimension to scalar. Okay, so even with this nonlinear function, this function is a linear of w. So this is one example, polynomial curve fitting with a scalar x. So this is not a vector, it's a scalar. Okay, and then this is the input x. This one is a scale of x, etc. And this is a linear function of parameter w. Okay, so this one is w transpose phi of x, and this is phi 0. Phi 0 x is 1, and phi 1 of x is x. Phi 2 x is x squared, etc. So this one is still linear of w, but we have nonlinear function phi. Okay, this is an extension of simplest model. And in the previous slide, I just talked about this polynomial function basis function, but that's not it. we can think of many other basis functions like a Gaussian and the sigmoidal functions. Okay, and I think you're already familiar with this Gaussian equation, and the sigmoidal function looks like this. Basically, this is one sigmoidal functions. Okay, if we change this mu j, then this function moves. Okay, and if we change this s, then it can change the shape like this, or we can have steeper. Okay, and the polynomial basis functions are global, which means when we put a small change in x, then all the basis functions will be affected by that change. Let's say x is here, the input x was here. Then if we change slightly, then this function will be affected, and this function, the value of this function will generate a different output. So look at these functions, and originally the value was something like minus 0.3. Then when we change slightly, now we have x dash, then the output is minus 0.5. Okay, so all the basis functions will be affected by this change. Look at these functions. Okay, and originally the value was around 0.2, and based on this change, then the output will be something like 0.4. So if you pick any basis function, all the functions will be affected by this change. And sometimes, when the x is around the 0, then these functions will not be affected. Some functions will not be affected, but in general, when x is some point around here, then all the functions will be affected. But these Gaussian or sigmoidal functions are local, because if x is around here, then look at this red function. If we change slightly here, then the red function doesn't change. Okay, the output of the red function is not changing. This one, the cyan is not changing, this purple is not changing, this green one, the blue one, they don't change. Okay, and the sum of them will be affected. This green one might be affected slightly, then the blue one will be affected, and the green one, then cyan. Some of them will be affected by this change, depending on the location of these basis functions. And this one too, sigmoidal functions are local too. So when the x is around here, for example, then these functions will be affected by this change. Okay, but this purple one will not be affected by this change. This blue one and the green one will not be changed. So depending on the location of these basis functions, if they are affected by the change, then they are. If all the basis functions are affected by small change of x, then the basis functions are global. Otherwise, they are local.